Imagine dropping a plastic package into water and watching it vanish like it was never there. It feels like magic, but this material is real, industrial, and already hiding inside products used by millions every day. The promise sounds almost too perfect for a planet drowning in plastic. Make the wrapper disappear, and maybe the problem disappears with it. That is the wastewater plastic. But this story is not about disappearance. It is about chemistry, infrastructure, and a dangerous human habit of confusing invisible with harmless. Because when this plastic melts into water, the real question begins: where does it actually go? And more importantly, what survives after the vanishing act is over? To understand that, we have to start with the polymer that made this illusion possible. A material engineered not to resist water, but to surrender to it on command. The star of this story is usually polyvinyl alcohol, also called PVA or PVOH. A synthetic polymer famous for being water-soluble. Unlike conventional plastics built to repel moisture, this one is designed so water can pull its structure apart. That strange behavior made it useful long before most people ever heard its name. Curare says its PVA film was commercialized in 1961 and later expanded into optical, packaging, and water-soluble applications. In other words, this was never a science fiction material. It was already part of the real economy. Manufacturers found it useful anywhere a barrier was needed for a short time and then needed to disappear cleanly. That simple trick opened the door to one of the most powerful product fantasies of the last decade. Convenience without waste, precision without mess, hygiene without direct contact. And from that point on, water-soluble plastic stopped being a niche polymer and became a cultural promise. The secret is not that the polymer hates being solid. The secret is that its molecular structure can interact strongly with water molecules. When the conditions are right, water penetrates the film, loosens the chain interactions, and turns a solid wrapper into a dissolved polymer solution. That is why temperature matters. Degree of hydrolysis matters. Thickness matters. Even the speed of dissolution can be tuned for a specific product and a specific use. Industry uses water-soluble PVOH films for unit dose products in personal care, agriculture chemicals, food ingredients, and pool treatments. The most famous example is the detergent pod, where a thin film delivers a pre-measured dose and dissolves during the wash. In hospitals, soluble bags can reduce handling of contaminated textiles before washing. In manufacturing, similar chemistry can simplify dosing, separation, and temporary protection. So the material is not a gimmick, because it solves real engineering problems with elegant precision. That elegance is exactly why the material spread so fast in the public imagination. A wrapper that disappears feels like the opposite of plastic pollution. It feels smarter, cleaner, more civilized. And in some ways, it genuinely is better than scattering solid plastic fragments across the landscape. It can reduce direct handling, reduce dosing errors, and reduce visible packaging waste in specific contexts. Researchers are also blending PVA with starch, cellulose, and other bio-based ingredients to push performance toward greener packaging. Some of these films are being explored for food packaging where transparency, barrier properties, and controlled degradation all matter. On paper, this starts to look like the future of responsible materials. But paper is exactly where many environmental stories look best. Reality begins when the dissolved polymer leaves the washing machine, the sink, or the factory floor and enters the systems we depend on to clean our water. This is where the story stops being magical and starts becoming technical. Dissolving is not the same thing as biodegrading. A material can become invisible in water and still remain a persistent chemical burden. OECD literature has described PVA as inherently biodegradable in certain tests, especially with acclimated sludge, which sounds reassuring until you notice the conditions. Those tests do not automatically mean rapid breakdown everywhere in the real world. A 2021 assessment found limited biodegradability of PVA-based materials under natural marine conditions, even though the tested materials did not show relevant ecotoxicity in that study. Wastewater treatment is another weak point. One widely cited US modeling study estimated that about 61% of PVA could end up in sludge and about 15.7% in the aqueous phase after treatment. That does not prove every product behaves the same way, but it destroys the fantasy that dissolution alone guarantees safe disappearance. Some reviews now warn that water-soluble plastics are often discussed as if solubility and sustainability were interchangeable, when they are not. This is the central tension of the technology. The cleaner it looks to the consumer, the easier it becomes to ignore what happens downstream. That hidden journey is exactly why the debate around soluble plastics exploded. In 2023, the US EPA formally responded to a petition asking for additional health and environmental testing on PVA, linked to safer choice products. That alone tells you something important. This material is not settled science in the public imagination anymore. It sits in an uncomfortable gray zone between innovation and unintended consequence. Industry points to performance, safety testing, and real utility. Critics point to data gaps, downstream emissions, and the risk of replacing visible waste with invisible pollution. Both sides are reacting to the same uncomfortable truth. Modern materials move faster than modern waste systems. We know how to sell convenience instantly, but we still struggle to measure everything it leaves behind. That is why soluble plastic is such a powerful documentary subject. It is not just a material. It is a test of whether our definition of clean is honest enough to include what we cannot see. Globally, the stakes are bigger than detergent pods. The same logic behind water-soluble plastic is shaping agriculture, packaging, textiles, and specialty manufacturing. The world is desperate for materials that behave more intelligently than the plastic of the 20th century. And to be fair, some versions of this technology may become genuinely transformative as formulations improve and testing becomes stricter. But that future depends on evidence, not enchantment. It depends on better wastewater design, better biodegradation standards, better transparency from manufacturers, and a better public instinct for asking what happens after something seems to disappear. So, when you see plastic vanish in water, do not think of magic. Think of chemistry, think of pipes, think of microbes. And think of a civilization trying to invent a cleaner future without lying to itself about where the mess goes.